I'm going to tell you a secret about the universe that will make you question absolutely everything you think you know about reality. And the strangest part? This isn't speculation. It's not cheap barroom philosophy. It's something every physicist on the planet accepts as proven fact, something tested trillions of times in laboratories around the world, something so fundamental that without it your cell phone wouldn't work. But I bet you have no idea what I'm talking about. And if someone has ever tried to explain it to you, you probably just nodded and pretended to understand, because it seemed polite to do so. What I'm going to tell you today is about something called quantum mechanics. But relax, I'm not going to throw equations in your face or make you memorize complicated names. I'm going to show you exactly what this thing means, why it's absolutely crazy, and why, even though it's crazy, we know it's true. Let's start with a simple question. What are you made of? Ah, Feynman, what an obvious question, you might say. I'm made of cells, which are made of molecules, which are made of atoms. Perfect. You paid attention in school, but now comes the interesting part. What is an atom? You probably have a mental image of an atom, that classic image of tiny balls, electrons, orbiting around a larger ball, the nucleus, like planets around the sun. This image is in every textbook. It's in the logos of technology companies. It's even become a universal symbol of science. There's a small problem. It's completely wrong. Electrons don't orbit the nucleus like planets. They aren't even little balls in any sense that makes any sense. And here begins our journey into the territory of total madness. Let me show you why. Let's do a thought experiment. Actually, a real experiment that's been done thousands of times. Take an electron, just one, a single electron. Now put a barrier in front of it, a wall with two slits, two narrow holes side by side. Behind that wall, put a screen that lights up when an electron hits it like an old TV. Now you fire this electron towards the slits. What do you expect to happen? Well, the electron is a particle, right? A tiny little thing. So it has to go through one slit or the other. It can't go through both at the same time. That would be ridiculous. It would be like trying to go through two different doors simultaneously. So you do the experiment. You fire an electron. It passes through one of the slits and hits the screen. Boom, a tiny point of light. Cool. Now you do it again, and again, and again. Thousands of times. And gradually, a pattern begins to appear on the screen. And here's the problem. The pattern that appears isn't the pattern that should appear if the electrons were passing through one slit or another. The pattern that appears is called an interference pattern. It's the kind of pattern you see when waves interact with each other. Like when you throw two stones into a lake and the waves meet, creating regions where the water rises higher, constructive interference, and regions where the waves cancel each other out, destructive interference. But wait a minute. Electrons are particles, not waves. How on earth are they creating an interference pattern? The only possible explanation, and listen carefully to this because this is where things get sinister, is that each electron is passing through both slits at the same time. Each individual electron is interfering with itself. It exists in both places simultaneously. Like a wave, passes through both slits, interferes with itself, and then, when it hits the screen, behaves like a particle again, creating a single point of light. This is madness, you shout, and you're right. It's utter madness. Then you think, I'm going to catch these lying physicists. I'm going to put a detector at each slit to see which one the electron actually passes through. Great idea, let's do this. Put a detector at each slit. Now fire the electrons again, and the detector shows that the electron passes through one slit. Only one, never both. Every time you look, it's passing through one slit or the other, as any normal particle should do. Aha, you think. I knew it. Those physicists are charlatans. Electrons are normal particles passing through one slit at a time. But then you look at the screen behind the slits, and the interference pattern has disappeared. Now the pattern is exactly what you would expect from particles passing through one slit or the other. Two simple stripes, not that complex interference pattern. Let me repeat this very clearly, because it's absolutely crucial. When you're not looking, the electron behaves like a wave, passing through both slits at the same time and creating an interference pattern. When you're looking, it behaves like a particle, passing through only one slit and there's no interference. The act of observing changes the outcome of the experiment. It's not that the detector is somehow mechanically hindering the electron. It's not that you're unintentionally pushing it. It's that the very act of measuring, of obtaining information about which path the electron is taking, forces the electron to choose a path. Before the measurement, it doesn't have a defined path. It's literally on both paths at the same time. This is called quantum superposition. And it's not some creative philosophical interpretation. It's what experiments have shown repeatedly, without exception, for almost 100 years. Now you might be thinking, okay, but that's with electrons, which are microscopic and strange things. This doesn't happen with normal, everyday objects. And you would be, well, partially right. Large objects generally don't show obvious quantum behavior. But that's not because they follow different rules. It's because they are constantly being observed by their surrounding environment, air particles colliding with them, photons of light hitting them. These constant interactions cause what we call wave function collapse to happen automatically. But in principle, the same rules apply. And we know this because we can already see quantum effects in increasingly larger objects. Molecules composed of dozens of atoms showing interference, even small crystals vibrating in quantum superposition. The line between the quantum world and the classical world is becoming increasingly blurred. Here's another thing that will fry your brain: quantum entanglement. Einstein called it spooky action at a distance and hated the idea, but it turns out he was completely right. It works like this. You can create two particles in such a way that they become entangled. This means they are connected in a mysterious way. If you measure a property of one particle, say its spin, which is like a rotation, the other particle instantly knows the result, and its spin is also defined, even if it's on the other side of the galaxy. And when I say instantly, I mean instantly. Not at the speed of light, faster than light, instantaneous. But Feynman, you shout. You just told me that nothing can travel faster than light. Einstein proved it. Yes, calm down. You're right. No information is traveling faster than light. It's a technical subtlety, but it's important. You can't use quantum entanglement to send messages faster than light because you don't control the measurement result. When you measure your particle, you get a random result. It could be spin up or spin down, 50% chance for each. And the other particle will have the opposite result. But you can't control which result you get, so you can't use that to send information. But that doesn't change the bizarre fact that there is an instantaneous correlation between the two particles. It's as if the universe has a hidden sheet of glue, keeping track of entangled particles no matter how far apart they are. Einstein really hated that idea. He spent years trying to prove that quantum mechanics was incomplete, that there must be hidden variables, hidden information that predetermined the results, like marked cards in a deck. If you knew the hidden variables, you could predict exactly what was going to happen. And you wouldn't need this crazy story of particles that don't have defined properties until you measure them. In 1935, Einstein and two colleagues, Podolsky and Rosen, published a famous paper, now known as the EPR paradox, arguing that quantum mechanics had to be incomplete. The argument was clever and compelling, but in 1964, a physicist named John Bell discovered something extraordinary. He showed that if hidden variables existed, they would make different predictions of quantum mechanics in certain very specific experiments. You could test which one was right. And you know what happened when they did the experiments? Quantum mechanics won, without exception every time. Einstein's hidden variables were wrong. The universe really is probabilistic at the fundamental level. Particles don't really have defined properties until you measure them, and quantum entanglement really exists. Einstein was wrong, and he was wrong in the most interesting way possible. He was wrong about the universe being even stranger than he imagined. Now let me tell you about another absolutely crazy consequence of quantum mechanics. You can't measure anything with perfect precision, not because your instruments aren't good enough, not because you aren't careful enough, but because the universe itself doesn't allow it. This is called Heisenberg's uncertainty principle, and it's poorly understood by practically everyone who's ever heard of it. People think it's about measurement interfering with the thing you're measuring, like if you shine a light on an electron to see where it is, the light pushes the electron and changes its speed. There's a grain of truth to that, but it's not the whole story. The truth is much deeper. The truth is, particles don't have both a defined position and a defined velocity at the same time. It's not that they do, but you can't measure them. It's that they literally don't. The more precisely defined a particle's position is, the less defined its velocity is, and vice versa. This isn't a limitation of technology. It's a fundamental property of reality. Think of it this way. A wave has an interesting property. If it's spread out in space, you can measure its wavelength, which is related to speed, very precisely. But where exactly is the wave? It's spread out. It doesn't have a single position. On the other hand, if you want a wave that's very localized at a specific point, you need to add up several waves of different wavelengths, and then the wavelength becomes imprecise. And this has real practical consequences. For example, this is why atoms are stable. Think of an electron orbiting a nucleus. If the electron had a perfectly defined position and velocity, it would follow a well-defined orbit, like a planet around the sun. And then, because it is accelerating, changing direction, it should radiate energy and spiral into the nucleus in less than a picosecond. All atoms should collapse instantly. The entire universe would be a soup of atomic nuclei. But the uncertainty principle saves the day. The electron cannot have a well-defined position and velocity, so it doesn't follow a defined orbit. Instead, it exists in a kind of probability cloud around the nucleus, a quantum orbital. And these orbitals have specific energies, discrete levels that the electron can occupy. The electron cannot lose energy gradually. It has to jump from one level to another. And the lowest level, the ground state, is stable. The electron cannot go lower because there is no lower level. So literally everything that exists, including you, only exists because the uncertainty principle prevents atoms from collapsing. You owe your existence to quantum strangeness. Here's another one, quantum tunneling. Because of the wave nature of particles, there's always a small probability of a particle appearing on the other side of a barrier, even if it doesn't have enough energy to classically pass over that barrier. It's like throwing a ball against a wall and occasionally the ball magically passing through the wall and appearing on the other side. This sounds like science fiction, but it happens all the time. This is how the sun works. In the sun's core, protons are colliding with each other, trying to fuse, but protons have a positive electrical charge, so they repel each other strongly. They shouldn't have enough energy to overcome this repulsion and fuse. But through quantum tunneling, they occasionally do it anyway, and when two protons fuse, they release energy. This energy eventually reaches us as sunlight. Without quantum tunneling, the sun wouldn't shine. Earth would be a frozen rock floating in space. There would be no life. There would be no you. And quantum tunneling also happens in modern technology. Those tiny chips in your cell phone? The transistors inside are so small that electrons often tunnel through barriers that should block them. Engineers have to design with this in mind. Quantum mechanics isn't an abstract theory. It's literally making your Instagram work right now. Now I'm going to tell you about something that many people think they understand, but definitely don't. Schrödinger's cat. You've probably heard of it. It's that story about a cat in a box that's both alive and dead at the same time, right? People think it's a cute metaphor about uncertainty. It's not. It's a devastating critique of how profoundly strange quantum mechanics is. Schrödinger proposed this in 1935 as a thought experiment to show how absurd the standard interpretation of quantum mechanics seemed. It works like this. You put a cat in a box with a diabolical device, a tiny radioactive sample, a Geiger counter, a hammer, and a vial of poison. If a radioactive atom decays, a random quantum process, the Geiger counter goes off, the hammer breaks the vial, and the cat dies. If the atom doesn't decay, the cat lives. Now, according to quantum mechanics, before you measure whether the atom has decayed, it is in a superposition, decayed and undecayed at the same time. And if the atom is in a superposition, then the detector is in a superposition, fired and not fired. The hammer is in a superposition, fell and did not fall. The flask is in a superposition, broken and intact, and the cat is in a superposition of alive and dead. Schrödinger thought this showed that quantum mechanics had to be wrong or incomplete, because obviously cats can't be alive and dead at the same time. That's ridiculous. But you know what the problem is? The math works. The predictions of quantum mechanics are correct repeatedly, without exception. So either quantum mechanics is right and cats really can be in a superposition until you open the box and collapse the superposition, or there's something very subtle happening that we don't fully understand. The most widely accepted answer today is that large objects like cats are constantly interacting with their environment, air molecules, photons, etc. These interactions make continuous measurements, automatically collapsing the wave function. So in practice, the cat never reaches a pure superposition of living and dead. But in principle, if you could perfectly isolate the system from the environment, even a cat should obey quantum mechanics. And we know this is true because we've already managed to put increasingly larger objects into superposition. Giant molecules, tiny crystals vibrating and not vibrating at the same time. We're pushing the limits further and further. Here's the part that really fascinates me. Nobody agrees on what quantum mechanics means. Seriously. There are something like a dozen different interpretations, and brilliant physicists violently disagree on which one is right. The Copenhagen interpretation, the standard, states that particles don't have defined properties until you measure them, and measurement collapses the wave function. But what counts as measurement? Does it need to involve human consciousness? Can a rock make a measurement? Nobody knows. The many worlds interpretation states that there is no collapse. Every time a quantum outcome could be A or B, the universe splits into two branches, one where A happened and another where B happened. So, by measuring that electron in the double-slit experiment, you literally create two parallel universes. One where you saw the electron pass through the left slit and another where you saw it pass through the right slit. Each version of what you think you saw is a definite outcome, but both exist. Does that sound crazy? Absolutely. But mathematically it works perfectly, and it doesn't require that mysterious collapse. The price is having to accept that trillions upon trillions upon trillions of parallel universes are being created every nanosecond. There is also Bohm's interpretation, which states that particles have definite positions at all times, but are guided by a pilot wave that creates the interference patterns. This saves determinism, but introduces bizarre non-locality. The pilot wave needs to connect particles instantaneously across any distance. Which interpretation is correct? We don't know. And the frustrating part is that it may be impossible to know because they all make the same experimental predictions. They are just different ways of thinking about the same mathematics. But here's the crucial point. No matter which interpretation you prefer, the basic facts are the same. Particles really do behave like waves sometimes. Quantum superposition really does happen. Quantum entanglement really does exist. The uncertainty principle is real. Quantum tunneling is real. All of this has been tested, exhaustively, in millions of different experiments, and quantum mechanics is always right. It is the most precisely confirmed theory in the history of science. Some predictions of quantum mechanics have been tested with precision to 15 decimal places. It's like measuring the distance between New York and Los Angeles with a margin of error the size of an atom. So this is not philosophical speculation. It is not creative interpretation of ambiguous data. It is reality, repeatedly confirmed by experiments. And yet, almost no one really understands. People know the words. They know that electrons behave like waves and particles. They know there is an uncertainty principle. They know about Schrödinger's cat, but they haven't internalized what it means. This means that the universe at a fundamental level is probabilistic. There is no written script determining everything that will happen. There is genuine, irreducible randomness in the very structure of reality. It means that particles aren't just little billiard balls. They're something stranger. Something that sometimes acts like a wave, sometimes like a particle, something that can be in multiple places at once until you look. This means that observation is not passive. You can't simply take a peek at the universe without changing it. The act of measuring is inherently invasive, not due to technical limitations, but due to fundamental necessity. This means the universe is non-local in bizarre ways. Entangled particles know about each other instantaneously, across any distance, in ways Einstein called spooky, and that violate all our intuitive sense of how things should work. And here's the part that keeps me up at night. We don't know why the universe is the way it is. We know it is the way it is. The experiments are clear, but we don't know why. Why superposition? Why wave function collapse? Why is there a fundamental limit to measurement precision? Why entanglement? These are the rules of the game. We've learned the rules. We've become very, very good at using the rules. We've built quantum computers, created quantum cryptography, designed new materials using quantum principles, but we don't know who wrote the rules or why. And you know what? Maybe we'll never know. Maybe this is the fundamental structure of reality, and there's no deeper level. Or maybe there's something even more fundamental, some deeper theory that makes quantum mechanics seem obvious, in the same way that quantum mechanics makes classical physics seem obvious. Some physicists think string theory is the answer, that particles are actually tiny vibrating strings in 11 dimensions, and quantum mechanics emerges naturally from this framework. Others think loop quantum gravity is the answer. Still others think space-time itself emerges from something more fundamental, like quantum entanglement. Nobody knows. It's an open mystery. And that's beautiful. Because here's the thing about science. It's not about having all the answers. It's about asking better questions. It's about constantly refining our understanding. It's about being willing to accept answers that completely violate our intuition, as long as experiments support them. Quantum mechanics violates our intuition. It violates our common sense. It makes the universe seem crazy and incomprehensible. And yet it's true. Not because we want it to be, not because it's philosophically satisfying, but because it's what nature shows us when we ask the right questions. And that's what separates science from everything else. Science doesn't care about what you think should be true. It cares about what experiments show. And if experiments show that particles can be in two places at the same time, that measurement changes reality. That there is fundamental randomness in the universe, and then that's it. You accept it and move on. You build upon that. You make new predictions, you test those predictions, and little by little, piece by piece, you assemble an increasingly complete picture of how the universe works. So yes, science accepts quantum mechanics. Every physicist on the planet accepts it, because the experiments leave no choice, but almost nobody really understands it. And when I say that, I'm not being arrogant. I myself don't fully understand it. Nobody does. Feynman, one of the founders of quantum field theory, famously said, "I think I can safely say that nobody understands quantum mechanics." But not understanding it doesn't mean we can't use it. It doesn't mean we can't make incredibly accurate predictions. It doesn't mean we can't build technology based on it. It just means there are layers of reality that are still mysterious, that still defy our complete understanding. And honestly, that gives me hope, because it means there's still so much to discover. There are still profound mysteries waiting to be unveiled. There are still fundamental questions about the nature of reality that we don't know the answers to. And perhaps you, reading this now, will be the person who finally understands, who will see some connection that everyone else missed, who will discover the deepest layer of reality beneath quantum mechanics. Or maybe not. Maybe you'll just appreciate a little more how wonderfully strange the universe we live in is, a universe where particles can be in two places at once, where observation changes reality, where genuine randomness exists at the fundamental level, where particles can be connected across infinite distances in ways that defy all intuitive explanation. This is the real universe, not the universe we learned about in elementary school, with little billiard balls hitting each other, but a much stranger, much more interesting, much deeper universe. And the most incredible part, it works. This crazy, counterintuitive universe which violates all our expectations, it really works. Atoms are stable, the sun shines, your cell phone works, all because of these strange rules that nobody really understands, but that nature follows perfectly, without exception, trillions of times per second. Science accepts this, but almost no one understands it. And perhaps that's okay, because the universe doesn't owe us an explanation that makes intuitive sense. It simply is what it is. And our job is to discover what it is, not to insist that it should be something more comfortable.